So this lesson is on arithmetic sequences. So it's just a continuation on sequences, and this time we're going to focus on a particular type of sequence. So as a warm-up, let's do an exercise on a review on recursive formula. So remember, the recursive formula sort of has an initial term, initial condition, and then a term is defined based on what the previous term or terms are. So in this case, we're going to list through the first four terms of this recursive formula. So the first term is easy. We're given that as 3. But the second term, t2, is really going to be 2 times t1. So in other words, when n is 2, it's going to be 2 times the first term squared plus 1. So 3 squared is 9 times 2 is 18 plus 1 is 19. So that's the second term. For the third term, t3 is going to be 2 times t of n minus 1. In this case, the second term squared. So 19 squared times 2 plus 1 is 723. And then the fourth term is a lot trickier because the numbers get a lot bigger. So we see the general pattern here is that the next term is going to be the previous term squared. So in this case, 723 squared multiplied by 2. We add 1, and we plug that in our calculators, and we get 1,045,459. So that's the first 4 terms of that sequence. Here we're given a sequence, 3, 7, 5, 9, 7, 11, and we're asked to sort of come up with either explicit or recursive formula. So this one looks a bit tricky because we can't sort of establish a pattern between 3, 7, 5. Seems like it goes up 4, goes down 2, goes up 4, goes down 2. So that's sort of the general pattern that we could see. But how could we sort of come up with a general a recursive formula or an explicit formula? The first one I'm going to do is actually the more easier one. If actually we break the sequence down into 2, we could see a little bit better. So maybe I'm going to highlight the first, third, and fifth terms, and we can kind of see a pattern there that it's going up by 2. So for this one, I'm going to say that, well, the first term is going to be 3. Then the next term, so in general, t of n, is going to be, well, not the previous term, but the term before that, 2 terms before that, plus 2. In this case, this is for when n is greater than 1, and when n is odd. So that's sort of defining part of the terms, and we guys say, well, in this case, t of 1 is 3, and from there we could calculate t of 3, t of 5, t of 7. In other words, whenever we have the odd term in our sequence. Then we could break down the other part of the sequence. Is here we got 7, 9, and 11, and we could see that this happens as general as well. So here we could say that t of 2 is equal to 7, and sort of similar as t of n is equal to t of n, the second term before that, plus 2, and then for n is greater than 1 when n is even in this case. So in sort of breaking it down, we could kind of see the two, but then we sort of discover, oh, these two definitions are the same. In other words, it doesn't matter if it's n is even or n is odd. So here we could just express this in general, that t of n is the second previous term before that, plus 2. Whenever n is greater than 1, we still need our initial conditions of t of 1 is 3 and t of 2 is 7. In fact, in this case, it's not talking about when n is 1, but really when n is greater than 2. So there's our general recursive formula between the two, and we could sort of have a start initial conditions of t of 1 and t of 2. We could do sort of apply the same thing for the explicit formula. So in this case, we're going to say that t of n is equal to, well, we can kind of see the patterns here. This is the first, the third, and the fifth. So in general, that's going to be whatever the n is, in other words, whatever term number it is, plus 2 for n is an element of the natural numbers, in this case only when n is odd. Likewise, we're going to do the green. In this case, t of n, well, here's the second, fourth, and sixth term, and we see the relationship that the actual term is actually 5 more than the term number. So in this case, t of n is going to be n plus 5. Again, when n is an element of the natural numbers, but n is even. So when we get t of 2, t of 4, t of 6 using that equation. So in this next example, we have a sequence of numbers for 11, 18, 25, etc. We want to know what the 100th term is. So one way we could actually do this is we do see a pattern. The numbers are going up by 7, or the terms are going up by 7 as we go up in term number. We could go off and list all 100 terms and determine what the 100th term is. That's the most efficient way to do this. So this is where our general formula, explicit formula, comes in. Is that we could say that in general, t of n is, well, here we're going to see the difference between each number is a 7. So we could almost see that, think of this as a slope. So 7n, and so we're going to take the 4th term and subtract the difference there, because we want to think of it, what's the 0th term, or we want to try to get the y-intercept of this linear equation. So in this case, 4 minus 7 would be a minus 3. And we could kind of see this works because t of 1 is going to be 7 times 1, which is 7 minus 3, which is 4. So in this case, now we want t of 100. So in this case, this means that n is 100 because we want the 100th term. So t of 100 is going to be 7 times 100 minus 3, which is 700 minus 3, which is 697. So pretty straightforward, and in fact this last example is going to lead us into arithmetic sequence. So we're going to define and understand what an arithmetic sequence is and the general term for an arithmetic sequence. And then if we were given a sequence, we could determine if it is an arithmetic sequence or not. So determine if it's an arithmetic sequence or not. So in order to do that, we need to know what an arithmetic sequence is, and if so, determine what the general term in recursive formula of it is. So for any arithmetic sequence, we should be able to determine or derive a general term in recursive formula. So what can we say in the numbers in the sequence that we had in the example above in the warm-up? So 4, 11, 18, 25, we can say there was a difference. There was a constant difference of 7 between the terms. Another obvious thing that we could say that the sequence starts with 4. And the ... implies that this sequence is an infinite sequence. In other words, it goes on and on. So those are the things that we would explore in class if we're together, but just through observations, hopefully that's kind of clear. So let's go through our definitions. In this case, what an arithmetic sequence is. This is a sequence that has a common difference d between the consecutive terms. So it has to be applied for every single term in there, that there's a common difference d. So because in this case of the above example that we have over here, this is an arithmetic sequence, we can assume that the pattern continues. That's what the ... means, and then we have a common difference of 7. The other thing that we sort of need to know is a general term. So this is almost exactly like the explicit formula, except it's just another expression or a term for it. So in this case, this is a formula labeled t of n that expresses each term as a sequence. So each term of a sequence as a function of its ordinal, So really where it is in the sequence, first, second, third, fourth, etc., etc. So we have a general term for that. So essentially it's really what we've already looked at before in explicit formula. So specifically, if we look at an arithmetic sequence, if we have A, we sort of define this variable A as the first term in our sequence, T of 1, and D is the common difference. In other words, what's the difference between each of the terms, and N is obviously an element of the natural numbers. Then we could define the general term to be this equation. T of N is the first term plus, and then we take how many terms there are minus 1, or what's the ordinal, what's the term number, minus 1 times D. We're actually going to get that term number. Another way, in the recursive formula for that, for arithmetic sequence, is really kind of straightforward, is that the first term is obviously A, and each term is really the previous term plus that common difference. So that's the recursive formula, and every arithmetic sequence is going to have this same recursive formula where T of 1 is the first term, T of N is the previous term plus that common difference. And finally, the last equation we come up with, and is really the one that we've been using all along to sort of come up with the explicit formula, is we sort of saw that D was the common difference was, if we look to plot that out, it would be a linear equation. Is really that's our slope. So that we could think of that that's our slope here. And well, what's the y-intercept? I always go back, well, what's the 0th term? Even though there is no 0th term, but that's how we get the y-intercept. In this case, B is going to be whatever that first term is minus common difference. And then we're going to go back one difference to sort of get the y-intercept in there. And so here we get that general term of f of n is dn plus b. And if you now we're going to just look at some examples for this. So here we have a sequence 3, 9, 15, 21. We want to determine if the sequence is arithmetic or not. So we have to look at the difference of every single one of our terms, and only then can we determine it's arithmetic or not. It's not good enough to look at just one difference or two difference, but every single difference that we're given in the sequence. So in this case, the difference here, 9 minus 3 is 6. The difference there, 50 minus 9 is 6. And the difference there, 21 minus 15 is 6. So we could say that this is an arithmetic sequence. So yes. Common difference is 6. So here let's write the explicit formula. So again, we sort of have to sort of memorize this. T of n is going to be A plus n minus 1 times D. So in this case, we know that A is 3. And then we just said the common difference above is 6. So our general term, or explicit formula, is A3 plus n minus 1 times 6. So I'm actually going to write the 6 in front of that. So it looks like that. Let me clean that up a bit. And the recursive formula for the sequence, well, as I said above, recursive formula is always going to be the same for an arithmetic sequence, where T of 1 is going to be the first term. In this case, that was 3. And T of n is going to be the previous term, T of n minus 1. And we're going to add our common difference, in this case, plus 6 for n greater than 1. The 100th term of the sequence. So here is sort of the benefit of the explicit formula. We could do this through the recursive formula, generate a sequence with a recursive formula. It's actually a lot easier because you don't have to do the calculations over and over again. But if you're looking for a specific term, in this case, a 100th term, it's much easier to use the general term. So in this case, let me write down a general term again. This is T of n is 3 plus 6 of n minus 1. So to calculate the 100th term, or when n is 100, that's T of 100 is going to be 3 plus 6 times 100 minus 1, which is 3 plus 6 times 99. So which is 3 plus 6 times 99 is really 6 times 100 minus 6. So that's going to be 594. So therefore T of 100 is 597. Let's have another example. So here we're told that we have an arithmetic sequence. Calculate what the common difference is. So 102 minus 85, that's 17. Let's confirm. The next one, 119 minus 102 is 17 as well. So that implies that D is 17. So now let's go back to our explicit formula. So here, T of n is equal to A plus n minus 1 times D. So T of n, in this case, A is 85. Plus n, well, now we don't know what term number 323 is, so that remains as n minus 1, but we do know the common difference is 17. So here, and this is sort of the tricky part is, we could replace T of n. In other words, what term number are we looking for? In this case, it's 323. So this is explicit term number that we're looking for. That's what T of n is. In this case, we're looking for 323. So here it's going to be 85 plus, I'm going to expand this, 17n minus 17. So 323 is, simplify this, and we got 17n, 85 minus 17, 85 minus 7 is 78, minus 10, 68. So here we're going to get 323 minus 68. That's 255. It's equal to 17n. Divide both sides by 17, and we get n is 15. So therefore, 323 is the 15th term of the sequence. So the nice thing about this unit is that we could sort of have an idea whether the answer is correct. We could easily plug in 15 into our equation, and hopefully we do get 323. More importantly, here I got an integer. The n has to be an integer, n has to be a natural number. If we get a decimal of some sort, then we know that we messed up either our equation or our calculations incorrectly, and we should go back and revisit what we've done. Next question, the sixth term in the arithmetic sequence. So we're told that there's an arithmetic sequence is 23, and the 13th term is 44. Determine the 99th term. Well, this seems like we can't do this because we're not giving a sequence. But we're actually given enough information that we could actually resolve this. The key thing that we're told here is that it's an arithmetic sequence, so we can make certain assumptions, and that the sixth term is 23 and the 13th term is 44. So just working from those two pieces of information, I'm going to show you that we can actually get the general term from that. So in general, a general term is going to be T of n is equal to A plus n minus 1 times D. And we're not given the first term, so we can't figure out what A is. We're not given the difference, so we can't figure out what D is. But using this information, the sixth term, in other words, when n is 6, the term is 23. So what we're saying over here really is that T of 6 is 23. So here we're going to say, well, we'll replace n with 6, so T of 6 is A plus 6 minus 1 times D. Well, T of 6, we're told, is 23, and our sixth term is 23. A, and let's simplify, 6 minus 1 is 5, D. Well, we're going to do similar with the other thing that we're given, so that we have two equations now because we have two unknown variables, in this case A and D. So here, this is really saying that T of 13 is 44. So let's go back to a general term. T of n is A plus n minus 1 times D. So here we're going to replace n with 13. In other words, we know what the 13th term is. A plus 13 minus 1 times D. And we know 13th term is 44. So this is going to be 44 is equal to A plus 12 minus 1 is 12D. So now we have our two equations. So I'm going to solve by elimination. So I'm going to take this as my second equation actually, and this is my first equation, because I kind of see that these numbers over here are a bit bigger. So here I get 44. So first equation minus the second equation, I get 44 is equal to a plus 12d, and I can subtract 23 is equal to a plus 5d. So this is kind of nice because my a's do eliminate already, they disappear. So here 44 minus 23, that's a 21, and 12d minus 5d, that's going to be a 7d. Divide both sides, that's going to be 7, so that d is equal to 3. So I know my common difference is 3. I'm going to plug that into this equation over here. So I'm going to get, so let me write this, that 23 is equal to a plus 23, sorry, a plus 5d. So that was our second equation. And I'm going to substitute d in, d for 3. So here is 23 is a plus 5 times 3. So 23 is a plus 15. So subtracting 15 from both sides, I'm going to get the a is 8. So in other words, our first term is 8. From all that, we have a general term. We can determine that t of n is 8 plus n minus 1 times 3, because that's my common difference. And now I can figure out what t of 99 is. So now I can figure out what t of 99 is. So t of 99 is 8 plus 99 minus 1 times 3. So that's going to be 8 plus 98 times 3. Is equal to 294. So t of 99 is going to be 302. And that's how we solve a problem like that. So arithmetic sequences isn't too bad. Hopefully the concept is straightforward, and you can sort of go off and do the homework, do these questions to sort of solidify this concept.